Hi there. Today we're going to look at part 2 of classifying chemical reactions notes. But before we do, let's take a couple of seconds, pause the video, and please predict the products for these two reactions and then balance the equations. Okay, so let's go ahead and go over this now. So our first reaction, two elements coming together, one's a metal, one's a nonmetal. So this is going to make an ionic compound. So our product is going to be based on the charges of the ions that each of these elements form. So aluminum makes an ion with a +3 charge. Chlorine makes an ion with a -1 charge. And so when we put these together, the formula for our product is AlCl3. And once we write the formula for the product, we can balance the equation. Let's see, it looks like we have the even-odd problem here in terms of chlorine. So I'm going to need to make both sides of the equation have 6 chlorines. So I'll put a 2 in front of AlCl3 on the product side and a 3 in front of chlorine on the reactant side. And then I do have to check on my aluminum there. So 2 aluminums to balance everything out. All right, our second reaction, this is 2 compounds. And so when we see a compound reacting with a compound, our reaction type is going to be a double replacement. And so in this case, we have our ion switching partners. So step 1 is to identify all the ions present. So potassium ion is there, carbonate ion is there. Carbonate has a -2 charge. Magnesium is a +2. And sulfate is a -2. When I put these together, I take the positive from the first compound and put it with the negative from the second. So my first product is going to be, balancing the charges, it's going to be K2SO4. I need 2 potassiums to make 2+ charges to balance the 2- charges of sulfate. And then my second compound is the positive from my second reactant with the negative from my first. In this case, the positives and negatives balance, so the formula is just MgCO3. Magnesium carbonate. Once I write those formulas, and when you're doing that, remember that the cation always comes first. So I put MgCO3, not CO3Mg. After I do this, I can worry about balancing the equation. Let's see, 2 potassiums, 1 carbonate, 1 carbonate, 1 magnesium, 1 magnesium, 1 sulfate, 1 sulfate. It's all balanced. All right, now, what we're doing today is talking about 2 new types of reaction. One is a combustion reaction and the other is a single replacement reaction. Right? And we want to be able to predict products and also utilize something called the activity series, which I will explain to you. Okay, what do these reactions have in common? Well, if you look closely at all of them, right, they all contain one element and one compound on both sides of the reaction. So we have an element and a compound reacting to form a new element and a new compound. This type of reaction is called a single replacement reaction. So in a single replacement reaction, one element replaces another element in a compound. So the general equation looks like this. A plus bx yields ax plus by. Now, we have to be careful here because the element involved can either be a metal or a nonmetal. And so what gets replaced depends on whether we have a metal or a non-metal. So if the free element is a metal, it's going to replace the cation in the compound because metals all form cations, all have a positive charge. So it replaces the positive portion of the compound. And if A is a non-metal, then nonmetals form negative ions, anions, so it will replace the anion in the compound. So first step, kind of think about what's going to be replaced. Let's look at an example of a single replacement reaction. So here we have a solution of copper to sulfate, and an iron nail has been placed into it. And if this reaction goes for a little while, then what we see is the blue color of the copper 2 sulfate kind of disappears, and it's replaced with a greenish color solution, and that's going to be containing iron 2 sulfate. Okay, and then if you look at the nail, on the left, it's all sort of irony colored, but as time goes by, the nail starts getting coated with orangey brown coating, and that is some copper. So in this reaction, the iron is replacing the copper from the copper 2 sulfate solution. So our equation would look like this. Fe plus CuSO4 yields Cu plus FeSO4. So what is happening? The iron is kind of kicking out the copper. We have the copper all by itself on the product side, and now the iron is part of the compounds. Okay, let's look at some more examples of single replacement reactions where we are going to be predicting the products. So in this reaction, we have as our free element magnesium. Magnesium is a metal, and so it's going to replace the metal ion from the compound. So when we put these together, we have to think about the charges that ions form. Magnesium makes a 2+ charge. It's going to combine with that nitrate, which is a -1. And so our compound, our new compound, is going to be MgNO3, 2. And then that will leave iron as our free element. Now if we take a quick look, it appears that everything is balanced, so I don't have to add any coefficients. Now, similar but slightly different situation is this one, where instead of our free element being a metal, it is now a nonmetal. And so chlorine makes the chloride ion, which is an anion, so it's going to replace the anion in the compounds. So the chloride will be combining with the sodium. Our compound will be NaCl, and then the bromine will become our free element. Since bromine's a Hofbrinkel, we need 2Br2. And then we have to look and see if we need to balance this equation, and we do. There are 2 chlorines on the left, so 2 in front of NaCl on the right. That gives me 2 sodiums, so I'm going to put 2 in front of NaBr on the left, and that balances everything out. Okay, let's do one more reaction. In this reaction, we're going to put some copper wire into silver nitrate solution. So the solution starts off clear and colorless. The copper has a little orangey color to it. But as this sits around, the copper wire starts to look a little bit fuzzy, kind of like a pipe cleaner. And the solution starts to take on a blue tinge. Now you guys remember from our lab what that blue color means. That's the color that copper ions are in aqueous solution. So the copper is actually turning into an ion, and that compound that it makes is dissolved in the water. So let's see if we can predict our products here. So we know that the copper is going to make an ion. The most common copper ion is the 2+ ion. So that will be combining with the NO3- to make CuNO3 AQ. So that's dissolved in the water. And then the fuzzies that are growing there are actually silver. And we can put in the state symbol now because we can see what's happening. The silver is a solid. So we just made ourselves some silver metal. Pretty cool. What's going to happen this time? Now we're going to put some silver metal into a copper nitrate solution. Will the same thing happen? Well, if you think carefully about what our products in our last reaction were, they were copper nitrate and silver metal. So obviously if we do the reverse of this, if we put some silver into copper nitrate solution, nothing's going to happen. There's no reaction. So it turns out that some metals, right, kind of want to be, are a little more excited to be a metal, a free element, and other metals are a little bit more excited to be an ion. And so in this case, copper likes to be an ion more, and silver likes to be a metal more. And what we've done here is made our own little mini activity series. An activity series ranks the elements based on how reactive they are. So copper is more reactive than silver, and that means that copper is going to be above silver on the activity series. So the activity series goes from most reactive at the top to least reactive at the bottom. Copper is more reactive than silver, and so it goes above silver on the activity series. Let's try a few more combinations. So I'm going to try some more combinations with copper and with magnesium metal and with zinc metal. And each of those will be reacted with these three solutions, with a copper sulfate solution, with a magnesium sulfate solution, and with a zinc sulfate solution. So let's see what that looks like. Okay, here's the little samples of metal. They're in a little glass spot plate. So those are like little dips, and I have little bits of metal in there. And you can see that the copper just looks kind of dull, like an old penny. It's hard to see its orange color, but it's there. The magnesium is little spirals, but they're definitely silvery colored. And the zinc is also little silvery colored bits. So let's see what happens when we put some solutions in with these. Okay, now we see that the solutions have been added into the metals. And remember, our copper sulfate solution is a blue color. So we're seeing that blue color here. But if we look across on copper, nothing has really happened, right? The copper metal still looks kind of the same as it did before. When we look at the magnesium, in the first well, it's gone from really silvery to dark. The middle well looks unreacted, and that kind of makes sense because here we have magnesium metal reacting with magnesium ion, and that wouldn't be a reaction at all. But with the zinc sulfate, we again see it's gone from silvery to dark. When we look at our zinc metals, the only one that seems to have gone away from silvery is the very first one. So what we've done here is we can look for the color changes to see where there's evidence of a reaction. Okay, so we can kind of summarize in this table where we see evidence of a reaction. So copper and copper sulfate, no evidence of a reaction. All the way across, the copper didn't react with any of those solutions. The magnesium metal did show evidence of a reaction with the copper sulfate, but not with the magnesium sulfate, but again, it did with the zinc sulfate. And then the zinc showed evidence of a reaction with the copper sulfate, but nowhere else. So how many reactions for each metal? Well, copper had no reactions, magnesium had 2 reactions, and zinc had 1 reaction. So here's our little summary, and let's turn this into an activity series. So the more reactions that an element has, the higher it is on the activity series. So magnesium would go at the top because it had 2 reactions. Zinc would go underneath it with 1 reaction. Copper would go below, and then remember, we already had evidence that copper was more reactive than silver. So we have a little ranking here of metals from most reactive to least reactive. And this can be expanded to include whatever metals you want by doing similar reactions. Okay, so there's a more complete activity series on the right there. And so when we have a single replacement reaction, this activity series comes in handy because we can tell whether a reaction is going to happen or not by looking at the activity series. So for a single replacement reaction to proceed, the uncombined free element must be above the ion on the activity series. If the uncombined element is below the ion, there is no reaction. Let's see if we can apply the activity series here to a couple more reactions. So I want to know if calcium and magnesium are going to react. So I find calcium and magnesium on the activity series. my free element, uncombined element calcium, is above magnesium, so this reaction will go. I can write products for this reaction. So calcium makes a 2+ ion. My product is going to be CaSO4, and then my free element is going to be magnesium. What about this reaction? Magnesium sulfate plus zinc this time. Well, when I check on the activity series, zinc is below magnesium, and so since zinc is below, it's less reactive. Here we will have no reaction. And by the way, don't expect you to memorize the activity series. If you need to use it on the test, I will give it to you. So time for a joke. I told a chemistry joke, but there was no reaction. Bum. What about nonmetal activity? Well, for nonmetal activity, we're going to confine ourselves to discussing the halogens, because the halogens make their own little activity series on the periodic table. So when you look at the periodic table, fluorine's at the top. It's the most reactive of the halogens. Iodine's on the bottom. It's the least. And the activity series for the halogens then works exactly the same way as it does for the metals. The element must be above the ion for the reaction to go forward. If not, there's no reaction. So let's try a couple here. So when we look at chlorine on the activity series, it's going to try to replace bromine. Since chlorine is above bromine, this reaction is going to go, and our products will be NaCl and Br2. I think we already wrote this equation, didn't we? Yeah, right? Okay. Then we can look at our second equation. How about iodine and sodium bromide? Well, this time iodine, the free element, is above the ion, and so in this case we will have no reaction. Okay, so that's all we need to say about single replacement reactions, and we're going to have one last type of reaction, and that's a combustion reaction. And this is going to be very narrowly defined. In a combustion reaction, oxygen combines with a substance and releases energy in the form of heat and light. And we are going to combine this to things that contain carbon. So something like magnesium we saw in class can burn, but we're going to call that a synthesis reaction. So when the carbon in coal burns, it combines with oxygen to make CO2. When methane in a natural gas fireplace burns, it combines with oxygen to make CO2 and H2O. We can have two kinds of combustion. There's complete combustion and incomplete combustion. And they're similar, but just a tiny bit different. So in complete combustion, all of the carbon gets converted to carbon dioxide. And incomplete combustion, some of the carbon there's not enough oxygen, so it gets converted to carbon monoxide instead. Okay, so complete combustion looks like this. The substance is completely burned when there's excess oxygen. So our hydrocarbon plus oxygen will give us the products, H2O and CO2. Right? So our hydrocarbon, things like alkanes, and we'll include alcohols, so made of carbon and hydrogen and sometimes oxygen, but those are the only elements that we'll have there. The other kind of combustion is incomplete combustion, and this happens if oxygen is limited, and it looks very, very similar. Right? The only difference is that instead of getting carbon dioxide for your product, you get carbon monoxide. So the only difference between complete combustion and incomplete combustion is whether you get CO2 or CO as your product. Right? And you'll be clued in to the question as to which of those to put in by whether it says there's excess oxygen or limited oxygen. And if it doesn't say, then just assume that it's complete combustion, because that's going to be more common. All right. So here's just a little table that kind of shows some of the differences between complete and incomplete combustion. You don't really have to write that down, but some of the things that you can tell is the color of the flame can help you tell. A blue color flame is complete combustion, a yellow flame is incomplete. So a candle burning, what color is the flame? Yellow, that's incomplete combustion, right? Smoke is more likely produced in a incomplete combustion scenario, right? So you can just kind of tell. Incomplete combustion is a little bit of a problem because the carbon monoxide, as I said before, is poisonous. But all combustion creates carbon dioxide gas, which is a greenhouse gas, which obviously isn't good. Okay, so let's wrap this up by showing a couple of examples. So here's what it would look like for a complete combustion reaction because we have excess oxygen. So ethane is an alkane. Monkeys eat peeled bananas, so that's 2 carbons. And then our number of hydrogens then is going to be 2 times 2 plus 2, so 6. We're going to put that together with O2. And since it's excess oxygen, we will make CO2 plus H2O. Then I'm going to balance my equation, 2 carbons, so I put 2 in front of CO2, 6 hydrogens, I put 3 in front of H2O. Uh-oh, I see this is going to be a problem. That's going to make an odd number of oxygens, so I have to go back and use my trick. I'm going to put a 2 in front of ethane, and that will make sure I have an even number of oxygens. So 2 times 2 is 4 carbons, 4 in front of CO2. 2 times 6 is 12 hydrogens, so 6 in front of H2O, and that gives me 4 times 2 is 8, plus 6 is 14 oxygens, so a 7 in front of O2. Takes care of that. And last example, right, methanol. This is an alcohol, because it ends in OL. Meth means just 1 carbon, so my formula then is C and then H, 2N plus 1, so C3, CH3OH, combined with oxygen. Since oxygen is limited, I'm going to make CO instead of CO2 and H2O. And then I can go back and balance 1 carbon, 1 carbon. 3 plus 1 is 4 hydrogens, so 2 H2O, and that makes 3 oxygens. There's 1 right here and 2 right there, and so we're balanced. All right, so there you go. That's the end.